Radioactive material decay by giving off energy and matter at a characteristic rate. This rate is measured in half-life. The term half-life is defined as the time it takes for 1/2 of the atoms of a radioisotope to disintegrate. Iodine 131 has a half-life of 8 days. After one half-life, that is 8 days, 20 milligrams of iodine 131 ends up at 10 milligrams. After a second half-life, the 10 milligrams of iodine 131 decays to 5 milligrams. And after 3 half-lives, 2.5 milligrams of iodine 131 remains. The cycle goes on until all the radioactive material is decayed. Strontium 85, used for bone scans, has a half-life of 65 days. How long will it take for the radiation level of strontium 85 to drop to 1/8 of its original level? We can start with a certain amount m of the strontium 85 isotope, and after a certain number of half-lives denoted by simple n, 1/8 of the substance should be remaining. So if we calculate for simple n, half to the power of n is equal to 1/8, that is 2 to the power n is equal to 8. That means n is equal to 3. So it takes 3 half-lives for m amount of strontium 85 to become 1/8 of it. So 1 half-life of 65 days decays it to 1/2 m. Second half-life of 65 days decays it to 1/4 of the amount we started with, and after a third half-life the amount remains at 1/8 m. A sample of sodium 24 with an activity of 12 millicurie is used to study the rate of blood flow in the circulatory system. If sodium 24 has a half-life of 15 hours, what is the activity after 2.5 days? So we first have to find the number of half-lives in 2.5 days. So for that we have to divide 2.5 days, convert it to hours by multiplying by 24, and the number of half-lives n is equal to 4. So we start first with 12 millicurie activity of the radioactive substance, and after one half-life of 15 hours we end up at 6 millicurie activity. Second half-life goes and we end up at 3 millicurie activity. After a third half-life, the activity remains at 1.5 millicurie. After fourth half-life, the activity of the substance remains at 0.75 millicurie. The half-lives of certain types of radioisotopes are very useful. They allow us to determine the ages of very old artifacts. Scientists use half-life of carbon-14 to determine the approximate age of organic objects less than 40,000 years old. By determining how much of the carbon-14 has decayed, scientists can calculate and estimate the age of a substance. And this technique is known as carbon dating. Carbon-14 decays by very weak beta decay to nitrogen-14 with a half-life of approximately 5,730 years. Isotopes with longer half-lives, such as uranium-238, can be used to date even older objects. Radiocarbon dating was found by Willard Libby. Some examples of material that radiocarbon can determine the ages of are wood, charcoal, marine and freshwater shell, bones, peat, and organic bearing sediments. Cosmic rays that enter the Earth's atmosphere in large numbers produce carbon-14, and plants absorb this carbon-14 combined with oxygen as carbon dioxide in photosynthesis. Animals and people take in carbon-14 by eating the plants. The ratio of carbon-12 to carbon-14 in the body in a living being at a given time is nearly constant. However, at the moment of death, the amount of carbon-14 begins to decay because it's unstable, while the amount of carbon-12 remains constant. Carbon-14 degrades every 5,730 years. And by measuring the ratio of carbon-12 to carbon-14 in the sample and comparing it to the ratio in a living organism, it is possible to determine the age of an artifact.